Good day everyone. This video is for presenting our findings from Group 3 to the activity number 4, Effect of Waxing on Perishable Commodities. And our commodity that we choose is tomato. So to start, we have to remember that tomatoes are living tissues even after harvest. They continue to undergo physiological processes that unfortunately lead to degradation. Common issues we see are weight loss from transpiration, shriveling, and rapid ripening that shortens the selling window. Proper handling is vital to reduce these economic losses. So the goal of this activity is to determine how waxing affects shelf life, and also compare the ripening rates between our treatments, evaluate weight loss over time, and deepening our understanding of the scientific principle behind waxing. So, how does waxing actually work? Think of it as a second skin. So, scientifically, it serves three main functions. First, moisture retention. It creates a physical barrier that reduces transpiration. Second, metabolic control. It slows down the respiration by modifying the exchange of oxygen and carbon dioxide. And lastly, the ripening delay. By regulating the internal environment, it postponed the senescence or aging. Bonus, it is also gives the tomato the glossy, marketable shine buyers love. So let's proceed sa among methodology. So for our setup, we used completely randomized design with two replications to account for natural variations. We compared two groups, treatment 1, which is the wax, and treatment 2, the control. So, materials and procedures. Materials, uniform tomatoes, mineral oil for our wax, cotton, weighing scale, and camera for documentation. So, proceed na tayo sa procedures. Step 1, we selected disease-free uniform samples. Step 2, we applied the mineral oil using cotton. Step 3, we stored them in a well-ventilated area. Next is monitoring. We perform daily or weekly checks and weekly weighing to determine the percentage of weight loss. So the formula used for average color index or ACI is ACI equals the sum of n times color index over n, where n equals number of fruits per color index and n equals total number of fruits.
Good day everyone. So in continuation with this slide, this is the result of the waxing activity or the LLA4. This slide shows the weight loss of our activity. So as you can see, our treatment 1 reached the 200. This means that it reaches the 200 grams since this graph is yung number ani is about ni siyang weight loss in grams. Kaya ito ang gigamit man ni kay 250 grams naman siya per replicate. So ito makita nga ito ang treatment 1 and treatment 1 R1 and R2 makita na to no nga from 250 within 21 days of duration ato ma-observe nga gamay lang ang iyahang weight loss from 250 nag-reach siya to 200 up to 150. However, if you try to look on the other side, the treatment 2 R1 and R2 with a span of 21 days during the waxing activity, we can see the severe decrease, no? From 250 atong treatment to R1, nabot na lang siya og 90, tapos ang atuang R2 is naabot na lang siya sa 100. Therefore, ato ma-observe nga nagyay significant effect ang atuang waxing activity since iyahang na lisen ang weight loss during 3 weeks of activity.
So here's our documentation before waxing in treatment 1 and treatment 2. For during storage, in treatment 1 and treatment 2, mao ni siya ang color sa tomato. And here's the documentation at 50% non-marketable stage in treatment 1 and treatment 2.
So, in here in our discussion, why did waxing affect weight loss? The primary culprit for weight loss in harvested tomatoes is transpiration or water loss. Tomatoes have tiny pores called stomata and lenticles. By applying our treatment, we created a barrier effect. This tin effectively sealed those pores, lacking moisture inside the internal tissues. So this is why the waxed tomatoes maintained their turgidity and remained firm and heavy, while the control group became watery and soft. So how did waxing affect ripening? So ripening is a physiological process fueled by oxygen intake and ethylene production. Our coating created in what we called an internal modified atmosphere. It restricted the oxygen entering the fruit and slowed the release of carbon dioxide, and by slowing the clock of the fruit's metabolic rate, we delayed the chemical reactions that break down chlorophyll. So essentially, we inhibit the ethylene that triggers and turn a tomato from green to red and eventually to mush. So were these results consistent with theory? And the answer for it is absolutely, because agricultural science well documents that surface coatings extend the life of climacteric fruits like tomato. So our 3-day extension, a roughly 17% improvement, perfectly matches the expected success rates for basic waxing in tropical climates. So finally, we must acknowledge possible sources of error. In any field experiments, variables like initial maturity variance, where some samples might have been slightly riper at day 0, or ambient fluctuations, so in our ventilated storage area, could influence the rate of decay. However, the clear gap between T1 and T2 confirms that the waxing was the deciding factor. In summary, our study clearly demonstrates that post-harvest waxing is a highly effective intervention for tomato preservation. By looking at our data, we can conclude that the application of a surface coating successfully addressed the two biggest threats to tomato quality: moisture loss and rapid metabolic ripening. Specifically, the treatment maintained higher fruit weight and significantly delayed the color transition from the beaker stage to full red. Ultimately, we proved that this simple method extends the marketable shelf life of tomatoes from 18 days to 21 days, and a critical 3-day window that can mean the difference between profit and waste for local sellers. Now let's move on to the recommendations. So based on these results, our team proposes 4 key recommendations for the industry and future research. First, agricultural adoption. We strongly urge local farmers and distributors to integrate waxing for produce intended for long-haul transport. According to the Bureau of Plant Industry, post-harvest losses in the Philippines can reach up to 40% without such intervention. So waxing is a low-cost solution to minimize this market waste. Second, the wax variety. While we used mineral oil, further studies should evaluate alternative coating materials like beeswax or carnauba. Determining the most cost-effective and locally available alternative is essential for scaling this technology. Third, precise measurement. For future academic work, we recommend utilizing digital colorimeters and thermometers. Moving beyond visual indexing to objective quantification will provide a more precise understanding of ripening kinetics. And finally, an economic analysis. We recommend a dedicated cost-benefit study to measure the exact profit increase per kilogram of wax produced. Quantifying the return of investment for the wax application will be the final step in convincing stakeholders to adopt this technology. And that's all for our presentation.